Andreas Dilger has been involved in the development of Lustre since its inception. From early prototypes in 2000 before the founding of Cluster File Systems through Sun Microsystems, Oracle, and Wham Cloud, over the next 15 years, Andreas was one of the lead Lustre developers. After Intel's acquisition of Wham Cloud in 2012, Andreas moved into the position of Lustre Principal Architect, where he continues to lead Lustre feature development. Andreas studied electrical engineering and computer science at the University of Calgary. Ladies and gentlemen, please welcome Andreas Dilger.
Hi, today I'm talking about our plans for Lustre 2.11 and future versions. Peter Jones has covered what's arriving in 2.10, even though it's still a little bit in the future. It's not too far away. Just a quick recap. So multi-rail LNet, Amir talked about that. That's work continuing in 2.11. Progressive file layouts is a great feature, 2.10. ZFS work continuing, and 2.11 is also going to have some interesting features in addition to those continuing developments. Data on MDT is something that's been coming for quite a while. File level redundancy is a feature near and dear to my heart that's finally basically working today, and will be delivered in 2.11, or the first phase of it. More work with D&E for ease of use, and we've got some things already underway for 2.12 and 2.13. I personally don't like to tout features that are just an idea that we're talking about. I only like to talk about features that are actually, there's somebody working on it, or, we have concrete designs and things. There's Lustre is, first and foremost a file system that, goes fast, and, that continues to be the case. We're investing time and effort into, making sure that Lustre keeps pace with new hardware that's coming around. And today, we have pretty good specs. I'm not going to read everything out, but, we can do about what, one network interface can do, about what, is available. You can attach storage to servers, but, of course, storage is getting faster, networks are getting faster. So, we have to make improvements in these areas, and I think we're, doing a fairly good job. Multi-rail LNet is going to let us, and other work for OPA and InfiniBand, we can keep pace with, individual interfaces going, 10 gigabytes a second, but, more importantly, we can start scaling out the number of interfaces that we can have in a server. And, IOPS on both the MDS and the OSS, we're continuing to look at improving performance there. And one of the interesting areas that's coming in 2.11 is being able to handle small files efficiently, right? Having a lighter weight, or a more efficient I/O stack on the client to handle small writes and things. And so, in aggregate, I think we're doing quite well. I mean, each of these areas needs, concentrated work on a bunch of smaller parts. And so I'm going to go into what all of the different parts are. So there's, an area that Intel is investing in quite a bit is improving ZFS performance. And I don't want to, say that we're not interested in LDiskFS either. Most of the users still use LDiskFS. It's really more that ZFS was a lot farther behind LDiskFS in terms of performance, and it needed more care and feeding to get the metadata performance up. So it just, in the workloads that ZFS was previously involved in, database-y kind of user home directories, people aren't creating 1 million files, all in one shot. So we went from, 5,000-ish creates per second up to tens of thousands. It'd speculate maybe 30, 40,000 in 2.10, but we're going to keep on pushing that for 2.11, and work going into ZFS itself will help on that front. There's also other changes in the infrastructure of ZFS itself that we've been helping with hardware-assisted checksums and compression, and improving memory management. We contributed a little bit to that one through the Coral project. There's a bunch of other people. Not enough room on the slide to list them all, but that's been a big improvement for ZFS in the next release. Improved fault management, and like all of the ZFS ones, it's a community effort, right? It's a very good open project. So we had one of our dedicated developers working on that. Multi-mount protection is a very important feature that's existed in LDiskFS that Livermore is working on for, protecting failover and things with the ZFS level. And in 2.10, we had project accounting, project quota for LDiskFS, and we have a developer working on the equivalent functionality for ZFS so that you can have project quota for ZFS. There's other more significant features going in, probably not in the upcoming release, or definitely not in the upcoming release, but these are substantially finished today. And the declustered parity VDEVs for ZFS is a quite interesting thing, mostly for HPC, right? People are not going to have, very often 50 drive or 100 drive JBODs per server, in your business environment. But in the HPC environment, that's definitely of interest. And so that's a feature that's being developed in conjunction with Argonne National Lab. And the other one, metadata allocation class, allows you to store, ZFS internal metadata on either separate disk devices in mirrored mode compared to, RAID, or on separate, physical media like SSDs, which I think most people will be interested in. And so it's essentially like, a little Lustre file system inside the file system for ZFS now, right? You have a separation of data and metadata. It worked, it worked for us. Why shouldn't it work for ZFS, right? And, this improves not only your, file access, file create performance, but also scanning and scrubbing things that need to traverse all of the ZFS metadata. LNet, multi-rail, dynamic discovery, health network, I won't really cover that at all. But ongoing work for 2.11 and 2.12. Data on MDT, there's been a whole presentation on this, but it's actually, just wanted to highlight that this is a feature that is, really in the final stages of development for 2.11. With progressive file layouts, we had to do a bit of restructuring of the data on MDT code to integrate well with progressive file layouts. But it's really something that actually helped data on MDT to be more flexible. And so now, you'll be able to do things like, store the small files on MDTs, and you can specify it's at a megabyte, is it 64K or 32K, whatever you consider a small file. But you can store the first part of your file on the MDT, and if it grows larger, then it moves over to the OSTs and things like that. And, this is even if you're not doing small files, for many, HPC workloads, the beginning of the file is something like an index or whatever, and you might be fetching that, or some application metadata stored at the beginning, you don't have to read the whole file, and you can fetch this all from the MDT in a single shot, right? And so data on MDT is going to, reduce RPC overhead by, 2 or 3, 4 RPCs per file access, right? And you get size on MDS for free with this, and for small files. So it's really going to help in one of the sort of weaker areas for Lustre. My favorite feature is file level redundancy, and this really wouldn't have been at the stage where it is without the work that was done for Pervasive file layouts. They both share some infrastructure in terms of how to describe composite files, and while for huge sites they may not be interested in mirroring in your 50 petabyte file system triple mirrored, there's still a lot of value, I think, for HPC environments. You can do things like all files in Lustre. You could set a file system wide policy or directory wide policy for your striping. You can also set the mirroring on a per file basis, so you could say mirror 1 checkpoint a day or something like that, so that that's robust against an OST failure, because today, no matter how you slice and dice your file, is it striped, a large file striped over all the OSTs? Is it a file per process, that are all again written across all the OSTs? If one of the OSTs is down, you can't start your application. And, at least this way you'd have redundancy to start your application. You might lose some amount of computation, but, you would avoid having to wait for that OST to be brought up continuous, depending if it's lost permanently, you would have to restore from backup. Integration with a job scheduler, you can mirror your input files at the beginning of, being added to the job queue. And so, your application will be able to start no matter what the state is, right? And, this is the way that we can finally get more robust than what the individual hardware provides underneath us. So the first phase of development for file redundancy is what we call delayed mirroring. And essentially what that means is that there'll be, you can create your file, it will be written in an unmirrored form initially, and then there'll be essentially a daemon that's watching for files that need to be resynced. And so you won't get immediate redundancy, but within minutes of your file being created, you'd have a mirrored copy, and the client would be able to access either copy. Depending on if OSTs are available, it can make these decisions in a couple of seconds, depending on the average I/O round trip time. But the client doesn't really care how the mirror got created. It will just see that there's a mirror on this file. It timed out waiting for one OST. It can read the copy from the other OST. And so this isn't, I want to emphasize that the phase one is not mirroring for every use case and every application, right? It depends on what sort of reliability you need. It's definitely not intended to say you don't need RAID or failover or anything for your OSTs. But as we move through the different phases of development, there'll be more functionality added, right? Phase two is adding in what we call immediate mirroring, which allows the clients to write 2 or 3 copies of the file data immediately as it's generated, so you can withstand a failure at the time of writing. And it would still use the daemons and infrastructure from phase one to do resync if a OST goes offline during writes, but you would have your 2 copies right away. And there's more work to be done in terms of scaling out the resync engines to be parallel, handling, full OST failures efficiently, being able to specify, policies to say, files from this user or that are older than, a certain age, you can migrate them between tiers, right? And the last phase that we have, discussed is erasure coding. It's actually, not a super complex extension to the mirroring. This would again be a delayed erasure coding, so you wouldn't be generating erasure coded files right when you're writing them, but rather doing it as a post-processing step on dedicated clients or from the OSTs, and that would avoid having the double or triple overhead of mirroring, while still allowing clients to have reliable access to file data. On the other side, D&E has been in, the D&E 2 has been in Lustre since 2.8, 2.9, and so it's there, it's functional. There's still, usability improvements that we could make, and, we're starting to make them. One of the things that you can do today from D&E 1, you can migrate, a single directory from one MDT to another MDT or a directory tree. What you can't do today is migrate, from a single stripe directory to a multi-stripe directory. So that's something that, we already have a patch for, and we're reviewing that. This will, allow you to improve the performance of large directories that exist, if you didn't know at the time that, they would need to be striped. Taking that idea a little bit further, the automatic directory restriping is essentially the idea that if your file, you don't know in advance, it's the same sort of like PFL for directories, right? You don't know in advance how big this directory is going to be. Users typically, don't know these things in advance. They don't plan for them. And so your directory grows, a little bit large, 5 or 10,000 entries. We don't know what the threshold will be yet. But once it grows past a certain size, then you can automatically split the directory, and then users, won't have to do anything, but they'll start getting parallel performance from a single directory. You get better load balancing. You use your other MDT's performance automatically. And, it's possible for the, existing entries to be automatically migrated. They don't have to, but it makes lookups a bit more efficient. But these are all things that, happen, without the input of the user. And so I think that'll make D&E a lot more useful for people. I think one of the other things that we'll be looking at, we haven't really started development on this, but there's infrastructure in the code for it, to have MDT pools so that you can manage things like, certain users get this MDT, other users get another MDT, or you can have different classes of MDTs. Let's say with a burst buffer, you'd have a local burst buffer MDT with the burst buffer OSTs, and then, when the data moves off of the burst buffer, it's also migrated out of the MDT. There's a number of other miscellaneous features that are ready for 2.11. The client lock-ahead feature through LAdvise, so that applications, or more typically libraries, doing shared file I/O can get better performance by requesting, file write locks in advance of actually writing the data, so that they don't get false contention, because Lustre itself automatically expands file lock requests if there's not contention. And of course, the first client that opens a file says, hey, no contention on this file. It gets the full file lock, and then shortly thereafter, 100,000 other processes pile on and say, hey, I want that lock too. So if the application knows you're going to have an I/O pattern like that, it can be smart about doing this. And I don't expect people to change their applications. It'll be in MPI and things like that. Network request scheduler, DDN has had a discussion, and the University of Mainz to improve the flexibility and the ability of the servers to manage thousands of requests more efficiently and balance users' demands against each other. James just talked about the trace points, small file writes. So this is kind of one of the Achilles heels of Lustre is so the data on MDT will handle small files, right? But it's not necessarily improving the efficiency of small writes to large files. And so, we're starting to look into, making the client I/O stack and the method of handling, 4K, 8K, 16K size writes to be lighter weight and more efficient, so that you can just get higher IOPS through Lustre. And Seagate presented on LDiskFS improvements. Many of these are also similar to the ZFS work. It's being discussed with upstream developers, and we're actually just yesterday Google pushed one of the Lustre patches for large extended attributes, to go into the upstream ext4. So there's still good collaboration with ext4 development. I think we had a presentation from University of Mainz. University of Hamburg is doing ZFS compression, client-side compression, which is quite an interesting project. Lots of compute cycles on the clients. If you can send less data over the network, store less data on the disk, often you get a benefit, multiple benefits there. The global NRS scheduling and integration with cloud computing environments, big data is definitely interesting. So Intel is funding some of these. So there wasn't a presentation this year about this, but client-side compression is, I think, quite interesting. So they've actually, they're looking at using compression as essentially a cost reduction, right? So that they can get, specify a less, performant network, less performant disks, use the cycles that are, typically sitting idle while you're doing I/O on the client, and you can get a better throughput than what your hardware would otherwise allow, right? The compression speeds these days are, in the gigabytes a second, and, handling this efficiently from the client, integrating ZFS already has, the ability to do data compression on disk. So what we need is an end-to-end sort of integration of writing, compressed data on disk in a way that, you can access it efficiently after the fact. And, so they're showing, this is actually a Beijing Genomics Institute showing performance of gzip with ZFS. This is not Lustre, but this is just showing that, with no compression, you can get a certain speed that's basically limited by the speed of the hardware, but actually with some of the, LZ4, which is just a pure software implemented compression, you're exceeding the speed of the hardware. I don't want to tout Intel exactly, but there's, a compression hardware engine that is doing gzip as an offload engine, and, it can get fairly good performance. And at the same time, with the improved performance, gzip is very expensive. LZ4 is actually not very expensive, so that's the pink line at 20% CPU usage. With hardware offload, if you want to get, really high throughput, and still keep your CPU reasonable so that it can be doing all of the other things. And sort of longer term projects in terms of, 2.13, I think really that, we're just starting to get into the golden age of Lustre in terms of, we're getting all of these cool features, the functionality in terms of tiered storage, redundancy, policy engines, right? It takes a long time for an ecosystem like this to develop, but I think that there's lots of, interesting things that can just start to be done today. So the data tiering, metadata redundancy, we're just starting, sort of architectural level discussions about how do we mirror, data between MDTs. And I mean, the file level replication is important because you typically have, hundreds or thousands, maybe not typically, but some systems have hundreds or thousands of OSTs. And so the number of points of failure is very high. The MDT, it typically has better hardware, SSDs and things like this fails less often. But, it's still a single point of failure. So being able to mirror that data and provide availability even when an MDT goes offline is sort of the next thing that's getting attention. And so we're just having, some designing work done there. And so, I think the Lustre of the future is fairly interesting, right? I mean, as FLR, moves forward, having, totally non-redundant OSTs would be possible with erasure coding. You'll have different classes of storage, for different workloads, but it will be transparent to the application, right? You won't have to say read from or write from this directory if you need mirroring or burst buffer or whatever, and write to that directory if you need something else. I mean, it will be, one namespace, and the file system can manage the different classes of storage internally. And with that, I'm finished. Any questions?
Hi there. With the file level replication, or at least as it stands at the moment, how does it work when like an OST goes offline? Do all kind of updates immediately start going to the replica?
So in phase one, right, it's basically read only, right? So if you have a replica, if one of the OSTs goes offline, the clients will detect that through a timeout, or if there's an external health mechanism, the clients will detect that the OST is offline and immediately start reading from the other OSTs. In the phase two, when there's immediate write mirroring, it will be, it will detect again timeout, and the clients will notify the MDS that this OST is unresponsive. That OST will be marked, the component that holds that OST will be marked stale, and it will be logged into the change log. And so the writes will continue to the one or more other replicas of the file. And, when the OST comes back, the change log monitor process will resync the data from that. And so, I mean, there's going to be, multiple levels of improvement that you can do in terms of how efficient is the resync. Is it just a single threaded process? Is it running in parallel for large files? We've talked about having essentially like a dirty bitmap or something like that makes the amount of data you have to resync, reduced. Even with the PFL, you would only get right off the bat, you'd only get one component marked stale, depending on which OST it's on. So, you can improve the things. My philosophy is that, it's better to have the functionality there and then make it more efficient over time rather than, perfect is kind of the enemy of the good, right? So, does that answer your question?
Yeah, it does. Does it have any implication or any ideas down the road for how that might kind of affect or work with the HSM system? Because some of that kind of feature sounds really like what we would like, for instance, out of HSM in some ways.
Yeah, I mean, it's so in many respects, the tiered storage inside of Lustre will be a lot like HSM, right? You'll be able to do things even in phase one, like pull, make a mirror of your copy from your regular OSTs into like flash OSTs for burst buffer or something like that. So that could be managed by the job scheduler, and then the space managed in the burst buffer flash OSTs through HSM like it does, Robinhood can already do today, right? In terms of integrating with tape-based, if that's what you mean by HSM, even the progressive file layouts, I think, has a interesting ability that we could start doing like partial tape restores, right? You could have different components of your file, and you could restore the first megabytes or gigabytes of your file into one component and give it to the client to access, and then continue restoring into a later component while the clients are accessing the first part, as opposed to today, you get blocked on the full file access until it's restored, right? So there's definitely room for, improving the integration there, but it depends on, whether people are really interested in that or not, right?
Thank you.
Anyone else?
Okay, everybody's ready for lunch. All right, thanks.